before I jump to the second derivative, let me just address a question that came up in the break, which is just the nature of the nature of the parameters that you might see. Here I might know that there is very little change if I change x a little bit. But here I know that if I change x a little bit, there's a lot of change. Okay? And that, in problems like, let's say, climate change, that comes up all the time. So one of the standard topics is G. Here is the greenhouse gas concentration in the atmosphere, and this might be the damage, and damage here is broadly defined. It could be economic damage, or it could be other kinds of damage. The question might be, well, does it look like that? Does it look like this? Or does it look like that? Okay? And so clearly what really matters here is what's the slope, or what's the derivative of the damage function close to where we are. And so all kinds of analysis is done to try to determine whether the slope looks like this, or it looks like that, or it looks like that. And so much of the debate surrounding the costs and benefits of carbon dioxide mitigation really hinge on whether you think that the damage function looks like this or that. Okay? Okay. Now, the second derivative. So we all understand what the first derivative is. If you think of the first derivative not just as a slope, but as itself a function of x, then you might want to know, well, how does this function of x, the first derivative, how does its slope behave? Okay. In this example, here is a function f of x. I took its first derivative, and that first derivative happens to be a straight line. I could ask, well, how does the slope of this first derivative behave? And you'd probably have an easy answer, right? It's just a straight line. The slope of this first derivative is everywhere constant. Okay? And so it would actually look like anybody want to take a guess?
It's going to be
parallel to the x-axis. Is this correct or wrong? Wrong. Okay, it's negative, right? So it should be something like that. Why is it negative? Because it's downward sloping. Okay, so this is f prime prime of x. Okay. So this is the second derivative. That is, this is the slope of that slope, and that is the slope of that. Okay, so this function is the slope of that function, and this function is the slope of that function, but this function is itself a slope. Yes?
Is the second derivative always going
No. Just because I've shown you a relatively simple initial function here, that its first derivative was a straight line, and because its first derivative was a straight line, its second derivative was a horizontal line.
Whereas if you went back to the function,
If I went back to the crazy function, its first derivative looks a little bit more complex than that. Actually, it's even more complex than this. If I were to take a derivative of this, then I would get a function that's still nonlinear. And that too would have its own derivative, and that might still be nonlinear, and so on. Okay? In a sense, the amount of differentiation, the number of times you have to differentiate to get to a straight line, is a measure or a metric of the nonlinearity of a function. So when you see, when you're going to do your science classes or your climate classes and so on, you'll hear of highly nonlinear functions. Highly nonlinear, when we say highly or not so highly, that's determined by the number of times that you'd have to take a derivative to get to a straight line. Okay?
You do this until you get to a straight line?
Yeah, most functions, if you kept taking derivatives, you'd get very close to a straight line. It wouldn't necessarily. If you take functions that we can imagine in some random way, not functions that we've constructed specifically to be pathological, then if you just took some random functions that we constructed, you can almost certainly say that in a finite number of steps of differentiation you'd get to a straight line. But you could also construct pathological functions which don't converge to a straight line easily. And those are the kinds of functions that are used in cryptograms, in encryption. Because one of the ways of carrying out encryption is to look for derivatives of underlying random functions. Yes?
That's actually a very good lead into what I was thinking.
Sorry, what's your name again?
From Kathy.
Kathy, right. Kathy is going to be labeled as the philosophical one in your class because she's always giving me imponderable questions. But so it's a deeply philosophical question as to whether the functions that we see in nature are complex because there's noise. And that noise creates complexity, or because nature itself is complex and we don't know all the variables that affect it, so it looks like noise to us, but actually if we worked out or if we knew all the variables that affected it, it wouldn't look like noise at all. But that's beyond the scope of this, certainly this session. Okay, so what you want to know is the second derivative of a function is the derivative of the function. Okay, so it's a function that gives you the slope of the derivative, or the slope of the slope. And it also has its notation. F double prime x is the most convenient one, but you'll also see d squared y over dx squared, or d squared f of x over dx squared, okay, to denote that. And you'll see a third derivative too sometimes. Generally, you will not see the third derivative in economics, but you will see it quite a lot in biology and climate science and engineering. Okay. I haven't yet shown you what convexity and concavity mean, but just keep in mind that by definition for differentiable functions, if the second derivative is positive, then the function is convex. If the second derivative is negative, the function is concave. And you'll see what that means in a second. Okay? Okay. So here is a concave function. Okay. It's very common to see both students and instructors become confused about what's concave and what's convex. Part of it is that a concave up function is also referred to as a convex down function. And that terminology comes from pure mathematics. So we tend not to use that. Usually in applications, this is referred to as a concave function.
Is that concave up or concave down then? That's concave up.
That's concave up. So generally, in these applications, if it says concave, it means concave up. And usually what that means is that the greater than set, which is this set here, is concave. Okay? So you can try to remember it that way. Concave up means that the greater than set is concave. Or you can just get internalized that this is a concave function. Okay? Okay. Now, what is concavity? A differentiable function f is concave if its derivative function, its slope, is monotonically decreasing. That means it's always decreasing. Concave function has decreasing slope. Okay, let's go back and look at this concave function. Here it's steeply upwardly sloped. Here it's still upwardly sloped but more shallow. So its slope, while always positive, is becoming smaller. Okay? So that is a concave function. Slope is always decreasing. And, okay, convex function is just the opposite. Slope is always increasing. Okay, so what's going on here? Up here, the slope is steep but negative. So this is, the slope here is a large negative number. Let's say -8. Here, it's probably closer to -1. So its slope goes from -8 to -1. That means its slope is increasing. Here its slope is 0. And here its slope is positive. So slope is always increasing for this function. It's a convex function. Okay? Okay, an alternative definition that you will see of concavity and convexity has to do with intermediate points. Is this a concave or a convex function? Concave, right? For a concave function, if you take 2 points along the x-axis, let's say x1 and x2, and you evaluate the function at those points, you draw a straight line joining the two values of the function, that straight line will always lie below the function itself. Okay? That's a concave function. And you could, if you like to do logical proofs, you could play around. It's not a difficult proof to show that this definition of concavity is equivalent to this definition of concavity. Okay? And vice versa for convexity. But that shouldn't be your primary focus in this program. Okay. But this is a useful thing to keep in mind, actually. The reason I'm telling you this is not for you to do a proof, but because you'll find that this idea or this mathematical definition actually has quite a practical application. And you'll see that when we start doing economics, but it has to do with the values of averages. So here, for a concave function, the function evaluated at some average of x1 and x2 is always going to be higher than the average of the functions. Yeah, that was quick. For a concave function, the function evaluated at an average of x1 and x2 will always be higher than the average of the function of x1 and the function of x2. And that'll turn out to be a very useful application property when you deal with things like risk and its evaluation, and other applications too. Okay, yes. Yeah, so think of, let's say this is the average of x1 and x2. It's at the midpoint, let's say. Okay, then this is f of x2, this is f of x1, and this is f of x bar, which is the average. And this, okay, this is hold on. This is the average. I'm using Excel notation here. Okay? So that average of the functions is always less than the function of the average. Right, for a concave function. Yes. The average of the functions, okay, and that's this, the average of the functions is always less than the function of the average. That's the function of the average. That's the average. You go up till you hit the function, that's the function of the average. And this is the average of the functions, because this is the function here, that's the function here, and that's the average. Right, and that's the definition of a concave function. The secant, yeah, the secant here is always below. So, and when we went, if you go back and look at that secant line, tangent line thing, you'll see that that was a convex function, so the secant line was always above. Okay? Okay. Okay, now, so we're going to jump into the technical part of this, the differentiation rules. But before I jump to that, I want to make sure that you have at least an intuitive grappling. You don't have to have a grasp, but you have to have an intuitive sort of grappling with the idea of a slope, a derivative. Doesn't really matter about the second derivative too much. Okay? If you get that, then that's a lot. And in general, the way that, of course, the way knowledge is constructed, if you understand the simplest 20% of the material, then you understand 80% of the problem. And if you generally spend a lot of time understanding the last 20% of the problem. But when you learn, you should try to make sure you spend 80% of the time understanding the simplest 20%. Okay? So now this part is really all mechanical. And in real applications, you probably won't use it. That is, if you have a very complicated function, well, you're going to ask your computer software to determine its derivative, whether it's MATLAB or Octave or you're computing derivatives numerically. And if it's really simple, the only reason that you need to learn to take a derivative is for exams. And we all know that exams are not going to be your determinant of success in the endeavor that you've staked out for yourselves. So there's a lot of slides here, but I'm going to take you through them relatively quickly. But stop me if you want to. Okay, but some basic rules you do want to internalize. That is, functions, of course, might be sums of many different terms. And as such, when you differentiate, you can generally take the sums of the derivatives. That is, if you have a function that's the sum of two functions, its derivative is going to be the sum of the two derivatives. That is, you could take a derivative of each function and add them together, and you'd get the derivative of the original function. So, and you'll see, well, actually that's probably the next rule. The first rule is you can take each term, you can try to take a derivative of each term at a time, and the derivative of a constant you already know is 0. Right? The slope of a constant is 0. A constant function is a horizontal line. It has 0 slope. Okay. Okay, so another rule, when x is raised to the power of 1, then the slope of the coefficient the slope is just the coefficient on that x, right? So if y is equal to 2x, the slope of 2x is just 2. And what's the slope of 15? 0. So the slope of 2x plus 15 is 2 plus 0. Okay? Rule 3, when x is raised to some power n, greater than 1, but an integer, then to get the slope, you pull out the coefficient. This sounds more complicated than it really is. You pull out the coefficient, you multiply that by the power of x, you multiply that term by x, and you carry it to the power n minus 1. If I read that, I'd have no idea what that meant. But if you have done even a little bit of calculus, you'll remember that the derivative of xn is nx to the n minus 1. Okay, and that's all that that says. So you can see that sometimes it's easier to speak in mathematics than in English. Sorry? Right, which is the reason for this. Okay, which is why you want to spend 3 hours before Labor Day weekend doing this. Okay, so what's the slope of 5x cubed plus 10? Well, I guess I gave you the answer there. So that's 3 times 5 is 15 times x to the 3 minus 1. Okay, so that's 15x squared, and then the derivative of that is 0. Okay? For how many people is this completely new? A few of you, right? Okay. So what I want you to do is to make sure that you come and talk to me afterwards, or rather actually send me an email, and I'll make sure that we spend time separately. It's going to be obviously a small group, like half a dozen people. Certainly in my class, I and or a TA will spend time to help you do that, because it's obviously not something you'll learn in 5 minutes, and you shouldn't try to do it that way. Okay, but the little bit that you will need to get used to for problem sets or for exams, very little. In most exams, I give you very simple, if any, differentiation problems. I'll generally even give you very good hints. But just for the little that you do have to do, you should let me know so that we can spend some time, and so that you have enough to get through and get to the intuition. Learning this is not your purpose in life. Okay, hopefully that's clear to everyone.